Are you ready for our next laboratory together? Well, I hope so, because we're going to do it whether you're ready for it or not. How about that? So today we are going to be focused on recrystallization. Now, recrystallization is a technique in a laboratory that is done almost every other day, depending on what we do with it. So here's kind of the lowdown. This is what goes on in a lab. Number one, somebody tells me to make something. And I go, okay, give me the directions on how to make it. So they give me the recipe. They give me the back of the cake box. So I go into the kitchen, which is the lab. I read the back of the cake box, which basically tells me everything that I need to do in the order that I need to do it. And folks, that's exactly what I do. I follow the directions. But here's the thing. No matter how good I am in a laboratory environment, I will end up with a product. And this product will probably not be very pure. It's just the way things are. I know, it's kind of aggravating, but we have no control over certain aspects of what happens in a laboratory environment. So very often I am faced with this problem. And the problem is that I've just made a product. I have taken the time. I have followed the steps. I've done everything that I was supposed to do. And then I end up with this crappy product. And this product really needs to be cleaned up a little bit in order for me to use it. And that is the purpose of recrystallization. So what normally happens is that after I make this product, this impure product, I then will recrystallize. And when I recrystallize, this gets rid of all of the impurities that might be left behind in my product. And then I can go through the filtration steps, go through the cleanup steps, go through the next part of the laboratory procedure, and I will end up with a much purer product in the very end. Folks, that's the whole concept of recrystallization. And that's exactly what you're going to be doing in this lab. You're going to be focused on just recrystallization and performing the recrystallization the proper way. So what I mean when I say that, with recrystallization, step number one, make. You're not going to be making anything in this lab. What's going to happen is that you are going to start here. You're going to start at a product that was made that we're going to give to you. And that product is a very impure product. And we are going to focus only on recrystallization, which means I need to recrystallize, right? To get rid of impurities. And then when I get rid of the impurities, I bring this stuff back into a crystal, bring it back into a solid, and I will have a pure product because of that. All right, now let's kind of talk about some details here. First and foremost, we want to talk about the recrystallization technique in general, not with just this lab, but in general, broad terms, what does recrystallization mean? All right, well, I have a product, and this product is what I want, right? So here's my product. Here we go. There it is. I want that stuff. That's it. But I'm also going to have all of these impurities that will be mixed in. But you're going to say, well, where does the impurities come from? How do I know that I'm going to have impurities? You're always going to have impurities. Okay, that's just the way that it's going to be. And the reason is because in the production of this product, you have used more than one thing to make the product with. And very often byproducts could happen in these reactions, or byproducts, let's list those over here to the side. Byproducts, which are products that are made that we don't want. Number two, you could have remnants of solvents that are left behind. Number three, you could have remnants of reagents that are left behind. There's a whole number of different things that go on into this process when I make a product. And we have to get rid of all of those impurities. And that's what we're calling an impurity. We have to get rid of them. So it's nothing that I have control of. That's just the way the chemistry is going to go. That is just the way the reaction is going to go. I have no control of it. The only thing I have control of is how to get rid of it. All right, well, crystals. When I form a product, this product, the blue dots, right, it's going to start to form. And what happens here is that a solid is typically like a crystal lattice. And what I mean by that is that a solid has formation to it. Now, not all solids form crystals in the same way. That's very important for me to say. But for this purpose, I'm just going to draw the crystal as a grid. I think that you'll see it a little bit better if I do it this way. So when we make this product, if we had to make it, what I would see is a little molecule here and a little molecule there and a little molecule there. And they begin to maybe hook up with each other. And they hang out with each other. They like that. They're friends. They're buddies. They're going to hang out. Not a big deal. Not a problem. So I'm going to see a bigger and bigger crystal that could start to form. And it will get so big that I can see it with my eyeballs, right? And so we see that as a precipitate in the bottom of our flask or our test tubes or our beakers and so forth. But when this crystal begins to form, what happens in the very beginning is that sometimes, right? Sometimes, we get an impurity. And that impurity gets trapped into that crystal cage. And we get another one, and another one, and maybe another one. And we have to get rid of the impurities. The problem, though, is that it's embedded now into the product. The product is basically caging these impurities, and we need to get rid of the impurities. So what we do in recrystallization, step number 1, is that we have to dissolve, most of the time, my product again. I know, it's very annoying. I mean, here I've just maybe spent 2 or 3 days getting the product. I finally have this product. I see it in my flask. I begin to filter it, and I get this product on a filter paper, and I have to dry it to get a mass so I can report that mass. And then I have to recrystallize. That means I have to dissolve that all over again. I don't do the reaction again, but I dissolve it. So I completely put these crystals in solution. So what happens is that in my flask, I will have a liquid, and that liquid is typically some type of solvent that we call our recrystallization solvent. Now, sometimes this is fancy. Fancy means organic solvents that we get from a back flammable room. We bring those out. We have to, carefully handle them because a lot of times they're flammable. But sometimes this can be something just as simple as hot water. That's it. And that really depends on the type of product that we are forming. Do we have a inorganic product, a salt that can easily dissolve in water? Or do we have an organic product that has formed a solid that does not dissolve in water very well? Those are the 2 major issues that we always look at when it concerns the recrystallization solvent. So when I add the recrystallization solvent to it, sometimes I can just add the solvent, call it a day. But other times I want to heat this up. And this is very good for me. When I pick out a recrystallization solvent, what I really like to see here is the substance is soluble in the hot solvent, but it's insoluble in cold or room temperature solvent. And what this allows me to do, it allows me to take my product, there we go, and it allows me to take my impurities, and it allows me to dissolve them. And typically, I put it on a hot plate. And what happens is that this product will break up again. That's what I want. I want that crystal cage to break up. It formed maybe a little too fast in the very beginning, and because of that, it trapped those impurities that I did not want. So I heat this solvent up. It dissolves my product, and it frees back up those impurities. Those impurities go back into solution. And if I'm careful with the recrystallization solvent, I'm also going to pick out a solvent that doesn't precipitate. That is going to be the abbreviation of PPT. It doesn't precipitate my impurities back out. The impurities stay in solution. That is what we want with our recrystallization solvent. So if I take this product and I dissolve it, and it dissolves and it frees up the impurities, those impurities swim around in my flask, and they're going to stay in the flask because my recrystallization solvent hopefully will persuade those impurities to stay in solution. And then what happens is that I change the temperature. That triangle means change most of the time in a laboratory environment. So I'm changing the temperature, and typically I'll get colder, not hotter. However, it can go both ways. But most of the time we see a solution getting colder. And when that goes on, what I'll see is my product that I'm after clump together in the very bottom of the flask. It's recrystallized. It's now a solid again. But because my recrystallization solvent was chosen the proper way, my impurities will stay in solution. And then what happens from this point is that we filter. So by filtering, I keep all of the solid product that is now purified, and then filtering the liquid through has now removed all of my impurities. So we have a couple of terms that I like to just introduce. This product with the impurities, this is typically called our crude product. So when we talk about crude products in a laboratory, we're talking about an impure version of what we actually need. And then here in the very end, we are talking about our recrystallized version of that product, which should be a purer product, which should give me physical property tests that are much closer to textbook values. So boiling points, melting points, refractive indexes, densities, all of those should go much closer with a recrystallized product versus a crude product in the very beginning. All right, so this is the overall idea of recrystallization, and we do it very, very often, folks. I mean, every single thing that we do, it seems like if we're making a product, we have to go through a cleanup stage. We have to take our crude and we have to go to a recrystallized version of it, because if not, we're not going to get very good lab data in the very end. So, with that said, I want to kind of talk about the laboratory that you're going to be doing, which is a recrystallization laboratory specifically. So in this laboratory, we're going to be testing your recrystallization technique through the use of the vernier melt station. So this means that we are going to be looking at melting temperatures before and melting temperatures after. And we're going to compare these melting temperatures to see which one is closer to the true textbook value, to see if our recrystallization technique made any difference or not. So the industry connection that you're going to see on the very front page of this lab, it says you're employed with a food company, and they want to use benzoic acid as a precursor to a preservative. and that makes the products last a little bit longer on the shelf. So before they use the benzoic acid, they have to test the quality of the compound as it arrives at the facility that you're working at. So in the last batch of benzoic acid, your supervisor believed that the benzoic is contaminated. And the first test that will assess the impurity involves a melting point. So you're going to get a melting point of this raw stuff that came into the facility, and then you're going to report that melting product to us. And then it's probably questionable because they're already kind of telling you, listen, I think we've got a problem. We don't want to be putting poison into people's bread that we sell on the shelf. Okay, well, no, we don't, right? But we have to purify the compound using recrystallization to see if we get a better product and a better melting point. And if so, then we probably need to do this with the entire batch of benzoic acid that we've received at the facility. So the recrystallized product will be tested, and if the product is pure, the melting point of the crude and the recrystallized product will be very similar. All right, so this is how we know. Is it dirty? If it is, the melting points are going to be different. Is it not dirty? Is it good enough to use? If it is, then the crude product and the recrystallized product would be very similar as far as the melting point goes. So that's the idea and the concept of this lab that we're going to be doing. All right, so on this very first page, it's going to ask you a little bit about benzoic acid. Draw the structure on your sheet. What are the observations that you see with benzoic acid in the laboratory? And melting point temperature. What's the melting point as far as benzoic acid goes? All right, so there's benzoic acid. And this appearance, let me just make it clear, this appearance is what should it look like. All right. So these kinds of things you can find in reference textbooks. You can also find it online through something like Wikipedia. I hate to say that, but it's there. You can use it. So type in Wikipedia, do benzoic acid, and it will show you what this stuff is supposed to look like. So all of this is what it should be. What is the structure? What should the appearance be? And what is the melting point of the benzoic acid, pure benzoic acid, if we have it in the laboratory? All right, so procedure number one, we're going to wear some goggles. I don't think it's drastic. It's benzoic acid. It's a very common substance. It's pretty safe, but every time we're in the lab, we typically want to wear goggles. You're going to get the vernier melt stations. The reason for this is because we do multiple melting points throughout this process, and we only have one melting point instrument. So instead of everyone fighting over the MP50 from Mettler Toledo, we just bring out our vernier melt stations and let you use those again. So that way you've got one convenient near you where you're working. So we're going to connect the melt station and the LabQuest together. Number 4, it says prepare a sample for melting. So you're going to get a capillary tube just like you did before. You're going to put some of the benzoic acid sample that we provide you into, and this would be the crude, into the capillary tube, and then you'll put it into the melt station and you will record the melting point. When does it melt? And you'll record that temperature down. All right, so that's what step number 4 is basically going to tell you. All right, step number 5, in the first trial, you want to observe the melting process and make an estimate. So that means that this heating rate can go fast, okay? You don't really need to sit there and wait forever. So you might as well just crank up the system, folks. Don't waste time. Crank the system up, get a good idea of where this stuff melts, and then you might want to do it again for a second time, and then go a little bit slower. And that's what step number 6 is going to say. Now that you have a rough idea of the melting point, you're going to go back and you're going to do it once again, this time a little bit slower, in order to report a proper melting point. So first time is going to be the rough, and the second time you slow it down, both on the crude product side, in order to report a melting temperature. All right? Now, number 6 then says, okay, we're going to now recrystallize. So weigh out 1 gram of the benzoic acid sample. You want to make sure that you record the proper mass, because that's part of this process. We want to report impurity if there's any. Number 7, transfer the solid that I've just weighed out with number 6 into a 100 ml beaker and add 25 to 35 milliliters of hot deionized water to the sample. Okay, well, that sounds like that's my recrystallization solvent, right? I mean, here we've got this product. This product we think is crude. It has impurity with it. And we are adding hot water to that sample with the hopes of dissolving it and freeing up the impurity that might be behind. Then it says, number 8, place the beaker with the water on a hot plate until the solid has completely dissolved. Okay, folks, right here, ding, 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 ding. That's what I'm going to do because that's so important. And you would not believe how many times that I go into a lab and somebody says, is this done? Is this finished? Is this done? Am I doing this right? Okay, well, that's okay. But the problem that I always see with recrystallization is that you're asking me those questions and your solid hasn't even dissolved. So if the whole process of this is to free up impurity and your solid does not dissolve, how does your impurity get freed up? We need to use a little bit of common sense. All right? So number 8, you're going to put it on a hot plate and you're going to stir it and you're going to heat it until the solid completely dissolves in your flask, because up until that point, the impurity will still be in that crude product. So you have to heat, you have to stir, you have to continue to do it until the solid has dissolved in your flask. If you don't, and you're impatient, horrible numbers are going to come your way because you did not recrystallize. The only thing that you did was put your stuff in hot water. That's it. That wasn't recrystallization. That was just putting it in hot water and calling it a day. And that's not the purpose of this lab. So we'll have to get you to go back, and we'll have to get you to redo it. And I don't want you to redo it, and you don't want to redo it. So you have to make sure that this dissolves in a laboratory. Number 9, while heating, prepare an ice bath. Fill the beaker half full with ice, and then add some water to it. We're going to have to shock it. We're going to have to cool it at some point in time. So while you're heating this up, you might as well go get the ice. You might as well put some water in it and let it get really, really cold. Number 10, when the solid has completely dissolved, remove the flask from the hot plate and let it slowly cool. Now, look at this. Do you see that word right there? Right here? Slowly, slowly, slowly. Do not take the flask and dunk it down into the ice bath. I've seen people do it over and over. Do you know what's going to happen? If you take your hot solution with your product that you have just dissolved and you shock it and it precipitates, it will go too fast and it will yet again bring the impurity into the product. So what you've just done in previous steps was no good. It was wasted. Wasted time because you were so impatient that you did not allow your sample to slowly cool to room temperature before you put it in the ice bath. Why is this important? Folks, again, I've got this container, maybe a beaker, maybe a flask. I've got this solution in it of hot water. I want my solution to slowly cool so that way the impurities can stay in solution. And then my product will slowly start to form crystals here on the very bottom. They're not rushed. They're not stressed. They've got plenty of time in the world to solidify on the bottom. And I'll see that in terms of a precipitate. Another very good sign is that if my impurity is colored, then I will probably have a colored solution as well. So for instance, if my impurity looks a little bit purple and I undergo this recrystallization step and I see product on the bottom, but I see a purple solution that's still there, that is a very good sign that my impurity is staying in that solvent. And that is the whole purpose of using it. So that's what I want to see. After it goes to room temperature, then you put it into an ice bath. That is step number 11. So after it goes to room temp, which means that you can hold it with your bare hands and not go, ow, 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 ow. Then you're good to go. Put it into an ice bath from that point on. Now, here's another problem that we see. If no crystal growth has been observed, you scratch the inside bottom of the beaker with a glass stirring rod. And if no crystals still form, you'll heat the solution to evaporate some of the solvent, and that might allow the product to precipitate out again. So there's a couple of reasons for this. Too much solvent, folks, will prevent your precipitate from forming on the bottom just because there's too much solvent. And what's the definition of a solvent? A solvent keeps things in solution, so we've got to get rid of it. The next thing, if no crystals form, scratch it with a glass rod. Why on earth does that happen? Well, what's happening here with the glass rod, as you are scratching the surface of this container, you're kind of making these crystals that are in solution bump up against each other. And you need them to kind of get acquainted. You need them to come together. It needs to be a big family reunion. And all of these people need to coalesce around the same area. And scratching that surface rod and that friction will allow that to happen very often. Number 12, filter the solution, collect the crystals, and be sure to record the mass of the filter paper before you put it into the funnel. All right, that's very important. If you don't, how are you going to report the mass? You'll just have the mass of the product and the filter paper, and you didn't know what the filter paper weighed before. So you've got to do the filter paper beforehand. Number 13, once the solution's been filtered, allow the solid to dry at room temp. And when the solid is completely dry, record the recovered solid and record the mass, or weigh the recovered solid, and record the mass to the nearest 0.001 gram or 0.0001 gram, because we have analytical balances in the laboratory. Number 14, test the melting point of that product yet again. Number 15, make sure that you turn off the melting point system. Make sure that you box everything up and put it back to where you found it. Folks, that's it of the recrystallization. That's all that we need to do. Now, let's talk a little bit about the calculation here. In the beginning, I'm going to weigh out a certain amount of crude product. This crude product, though, will also have impurities with it, and I know that those impurities need to go away. I don't want those. So what we'll do is that we'll heat this up, and that's what we're doing in the recrystallization process. We're changing the temperature, and we're adding some solvent. And what we have now is going to be a big blobby of pure stuff. And then we'll have our impurities that are in the solvent. That gets removed. All right, so here's the deal. This is the pure or the recrystallized version, and this is the crude. So if the lab directions tell me to weigh out 1 gram of crude product, and that's what I do, with my pure, I will probably get a less amount. And the reason is because the crude includes the stuff I want plus the impurity. In the pure product, the impurity has been removed. So that means that my mass will probably go lower. And let's say that it's 0.800 grams. So after I allow it to dry, after I report my mass, I get 0.8 grams instead of 1, which is what I started with. That's fine. That means there's 0.2 grams of impurities. So we like to calculate a percent purity in a laboratory. And the way that we do that, if this is my pure, and I want to calculate percent purity, I'm going to take the mass of the pure stuff that I get, and then I'll divide by the starting weight that I used in the very beginning, and that gives me a fraction, a percentage, but this is a percent, so I have to multiply by a 100. And that's how we report percent purity. All right? So a couple of questions are going to happen on the data sheet. Here on the back side, you're going to see an area to write down your masses. So how much did you start with? What was the mass of your filter paper? What was the mass of the filter paper and the recrystallized product in the very end? What was the mass of just the recrystallized product once you subtract the filter paper from it? And what was the melting point of the recrystallized product, not just the pure? Number 3, based on the mass, how much impurity was in your sample? Number 4, compare the melting points. Which one was closer to pure benzoic acid in the textbook numbers? Number 5, calculate the percent impurity of your sample. We just talked about how to do that. And number 6, if a hot solution was immediately placed in an ice water bath during recrystallization, how might this affect the results? Well, we just talked about that. I think that you'll be able to answer that now. Number 7, in the industry connection scenario, you need it to report on the purity of benzoic acid. So based on your findings, is the benzoic acid pure? Why or why not? And number 8, the company places a strict purity standard on all of its products before they can be used. And the product needs to be greater than 98% pure. Does the benzoic acid pass the quality control criteria? Does it? Is it greater than 98% pure? And your calculations based on your masses will be able to help determine that. All right, and that's it of the lab, folks. That's all. So you're not making anything. You're not going through and adding things and mixing things together. You're just taking a product that's crude. You're dissolving it with hot water. You're making it slowly cool down to get a crystal. You're filtering off the impurities, and you're allowing this substance to dry. The other thing I want to say is that with this step of drying, you want to make sure that it is fully dried before you do anything else with it. And there's a couple of different ways that we can do that. Number 1, we might tell you to place it in the oven for a little bit. And the oven needs to be greater than 100 degrees Celsius. And the reason is because we want to drive off the water. And water boils at 100 degrees. So we got to get a temperature hotter than 100. Number 2, we might just say, put the acid in your lab drawers and let it dry over the next couple of days. And then the next time that we see you, it will probably be dry at that point. And this is going to be a room temperature drying. And then when you come back, you can get the mass and do what you need to do to finish up the lab after that point. So depending on how we're feeling, we'll let you know what to do as far as drying your product, whether it goes into the oven for 30 minutes or so, or whether we tell you just leave it in your drawer and come back and finish this lab up on a different date. So whichever way we'll go, that's what we'll tell you. Just ask. We'll let you know. All right, so good luck with the recrystallization. Again, be patient. Don't rush this process. If you rush it, you will not get good data. And that's really what this class is all about. It's the proper wet laboratory techniques. And in order for recrystallization to be proper, we have to make the necessary steps to ensure that we are giving these things time to dissolve and we're giving these things time to settle back out of solution in order to get a product. All right, so good luck. We'll see you in the lab when you get there, and hopefully you'll have fun doing it. I don't know. You might. Even if you do and you don't want to admit it, it's okay. It's all right. I know that you're enjoying it. You don't have to tell me with your evil eyes like, what are you going to get me to do next? You'd be surprised on what I see.